rules of inference. So the idea in this section is that we can connect logical statements together to make logical arguments and proofs. So here's a simple example. Example 1. If you have the key, you can open the door. You have the key, therefore you can open the door. Alright, so these two statements, the first is an implication, so it says if you have the key, then you can open the door. And the second statement says that the first part of that is true, you have the key. So then your conclusion is that you can open the door. Yeah, so in terms of logic, P is saying you have the key. Q, proposition Q, is saying you can open the door. Okay, so then in our example, if this implication is true and P is true, then we can conclude that Q must be true. Alright, so the first sentence here is this implication. Alright, so we're assuming that that's true. The second is that you have the key, that P is true. Alright, so those are they're called the premises of the argument. And then our conclusions, so if these premises are true, therefore Q must be true. Why does that make sense? Yeah, it's just from the idea of what this implication means. So remember, an implication is true. Well, it's always true if P is false, but if P is true, then it's true when Q is true, and the implication is false if P is true and Q is false. Alright, so if P is true and the implication is true, then the only way they can both be true is if Q is also true. Alright, so another way to think of it is in terms of this tautology. So P and P implies Q. That whole thing implies Q. And then this whole thing is a tautology, it's always true. Alright, so yeah, we can make it confusing, but the basic example was very simple. The first sentence says, if you have the key, you can open the door. Alright, so we're saying that that's a true statement. We're also saying you have the key, so that's true. Okay, so these two apply our logic, therefore you can open the door. Okay, so you need the key to open the door, you have the key, great, you can open the door. Okay, and we're using this symbol, this 3 dots like this, that means therefore. Okay, so this type of simple argument has a fancy name, modus ponens, Latin. Okay, so it says if P is true, and the implication P implies Q is true, therefore Q has to be true. And it's an example of a rule of inference. Okay, you're looking at the logic and seeing what must be true, what conclusion you can draw from the premises. Example 2. Suppose these statements are true. The first one says it is sunny, and the second one says if it is sunny, I wear sunglasses. What can you conclude using modus ponens? Alright, so it's sunny, and if it's sunny, I wear sunglasses. So therefore, you must be wearing sunglasses. Alright, so yeah, so it's nothing difficult. We can make it more confusing though. Example 3, suppose these are true. If it is sunny, I wear sunglasses. I am not wearing sunglasses. So can we conclude anything? Okay, so again, we're assuming that these two statements are true. So if it is sunny, I wear sunglasses. We're saying that's always true. And I'm not wearing sunglasses at the moment. So yeah, I think we can conclude something. Yeah, we can't use modus ponens. All right, but we can look a little more closely. Yeah, we know that something true implying something false, that's false. So the only way this implication can be true is if it is not sunny. Right, since that false implies false is true. So we can conclude that it is not sunny. Alright, yeah, so if it's sunny, I always wear sunglasses. I'm not wearing sunglasses, so then we can conclude that it's not sunny. Yeah, maybe a better way to see that it's not sunny, we can use the contrapositive of the original implication. So if it is sunny, I wear sunglasses. What's the contrapositive? Well, that says if I'm not wearing sunglasses, then it's not sunny. We know the contrapositive is equivalent. It's logically equivalent. Okay, so now we could use modus ponens. So I'm not wearing sunglasses. If I'm not wearing sunglasses, then it's not sunny. So therefore, it's not sunny. Yeah, these take some getting used to, but I hope it's making sense. But yeah, we can give this another name. So if you have an implication, P implies Q, and Q is false, or not Q is true, then not P has to be true. In other words, Q has to be false. Okay, so this variation is called modus tollens. Okay, yeah, so here in example 3, P is it's sunny, Q is I wear sunglasses. If it's sunny, then I wear sunglasses. If I'm not wearing sunglasses, then it's not sunny. Yeah, so this is like a contrapositive version of modus ponens. Example 4, if it is Monday, then Jose goes to the store. If Jose does not go to the store, what can you conclude? Okay, so P, so matching it to this, yeah, P says it is Monday. Q says Jose goes to the store. But if not Q is true, so if Jose does not go to the store, then not P must be true, so it's not Monday. Okay, so the good thing about, if you can remember modus ponens and modus tollens, then you can just match it to the template here. You don't need to really use any logic. Okay, another variation. Example 5. If it is Monday, then Jose goes to the store, right? The same thing. If it is Tuesday today, what can we conclude? All right, so if it is Monday, then Jose goes to the store. We have that information. But today is Tuesday. So what do you think? Yeah, so if your answer is that we can conclude that Jose didn't go to the store, that's an example of a fallacy or an incorrect argument. Yeah, we can't. If all we know is that Jose goes to the store on Monday, we don't have any information about what he does on Tuesdays. Yeah, he might go to the store every day. He might go to the store just on Mondays and Tuesdays. So our implication is only telling us about Mondays. All right, so it's they're called fallacies, but it's just you just have to be careful. Using the logic correctly. All right, so there's more rules of inference. Here's another one with another fancy name, hypothetical syllogism. So this says that if you have two implications, so if P implies Q is true and Q implies R is true, then you can combine them to say that P implies R must be true. All right, and that makes sense. You're just kind of connecting the arrows. So in this example, suppose these two statements are true. If it is Monday, then Jose goes to the store. That's the first implication. The second one is if Jose goes to the store, then he buys candy. Well, if those two are true, what can we conclude? Okay, so you can see what P, Q, and R are in this case. So we can conclude that if it is Monday, then Jose buys candy. Alright, so that's the P, that's the R. So it's understood that he goes to the store, and if he goes to the store, then he buys candy. So we can cut out the middle and just go from it being Monday to buying candy. Although, we have to be careful. So this is our conclusion. Can we conclude that Jose buys candy? No. We need to know what day it was. It would need to be Monday. Alright, so all we can logically conclude from these two is that if it's Monday, then Jose buys candy. We don't know if R is true. That depends on if P is true. And some more rules. So this is modus ponens. Some examples. This table on page 72. Is this visible? So each rule of inference is there's a tautology in the background. And so we have modus ponens, modus tollens, hypothetical syllogism. There's a few more here. So suppose P or Q is true, and not P is true. In other words, P is false. So if you have P or Q and Q is false, well, then Q must be true. If P and Q are both false, then that or statement would be false. Alright, so if you have P or Q and you know that one of them is false, then the other one has to be true. A simple one here. If P is true, well, then you can deduce that P or Q must be true. Or if P and Q is true, well, and just from the definition of and, then each of P and Q have to be true, so certainly P is true. Alright, so that's called simplification. Or if you know that P is true and Q is true, then P and Q is true. So these ones are very simple. This one's more interesting, called resolution. So if P or Q is true and not P or R is true, well then Q or R must be true. All right, and yeah, that's fairly easy to see. If P or R is false, that means that Q is false and R is false. Well, if Q is false and R is false, then one of these two has to be false. So if these are both true, then either Q is true or R is true. Yeah, this an example of that here. So suppose today is Monday or Tuesday. So that's a true statement. Another true statement, today is not Monday or it's Friday. So what can we conclude? Well then, by resolution, it must be true that today is Tuesday or Friday. Alright, so it's a little bit like those Mondays canceling. So if today is Monday or Tuesday, and today is not Monday or it's Friday, well, yeah, it has to be Tuesday or Friday. Yeah, why couldn't it be Monday today? So yeah, well, yeah, if it's Monday, then yeah, this first one is true. But then this would be false, or it's Friday. Yeah, so it can't be Monday, because if this last one is true, then that's telling us it has to be Friday. Okay, so yeah, we can rule out Monday. And yeah, this is the resolution rule of inference. And we can use these rules to make longer arguments. Alright, so suppose, for example, that P is true, that P implies Q is true, and that Q implies R is true. Okay, so these are all true. Okay, what can we conclude? Well, we can apply modus ponens to these two and get that Q has to be true. And then apply that to Q. So we know Q is true. Also the third one, Q implies R. So that apply modus ponens to that. We get that R has to be true. Alright, so just using modus ponens twice, we get that Q has to be true and R has to be true. Yeah, we can also we could apply a hypothetical syllogism, combine these two implications to get that P implies R, so we can we could have used that as well. Yeah, if you have a longer string of implications, so if P is true, and P implies Q is true, and Q implies R is true, and R implies S is true, well, yeah, keep applying modus ponens, then you get that Q, R, and S have to be true. And yeah, this is a famous method of proof called induction. Yeah, this is just the first part of it. Yeah, if you can in fact make an infinite string of these arrows and prove infinitely many things are true using this idea. So yeah, that's called induction. Covered in chapter 5, yeah, CSI 35, we look at induction. But yeah, it's just based on this modus ponens, just repeating. Okay, how about example 7? Suppose these expressions are all true. So not P implies Q, P implies R, and not Q and S. Use the rules of inference to show that P, R, and S are all true. Alright, so let's start with that bottom one. So not Q and S is true. Well, yeah, the only way two things connected by an and are true is if they're both true. So not Q is true and S is true. Yeah, that was called the simplification rule. Alright, so now we can... Okay, so we've used our logic, so we worked out that not Q is true. And now we're going to combine that not Q being true with the first implication. So we have not Q, and not P implies Q. Alright, so if you remember modus tollens, that says that not P, in other words, P has to be true. Yeah, so instead of just having a P here, we have not P. Let's go back. Where was modus tollens? So yes, if P implies Q and not Q, then we have not P. So in our example, yeah, we have a not P here. So we have two nots, so those cancel out, so we just have a P. You remember the double negation rule. Alright, so P is true. And then one last bit of logic. So P is true, and we have this the second implication, P implies R. So by modus ponens, R has to be true. Alright, so yeah, we showed that S is true, P is true, and R is true. And that's what we wanted to prove. Also Q is false. Yeah, not Q is true. Alright, so yeah, we're just yeah, again, these are called the premises. And so we assume that these are true. these are the premises. So you assume that these are true, and then this is our conclusion. That so if we assume that these implications and this and, that these are true statements, then using the rules of inference we can conclude that P, R, and S must be true. Alright, so that's the idea.